We present Unaligned 2D to 3D translation with conditional vector-quantized code diffusion using transformers. Given 2D images as input, our method generates high-quality 3D samples of complex data exhibiting both varying outer and internal topologies with different material properties and domains. For instance, medical computer tomography scans from X-rays and security baggage screening at airports. In contrast to natural images or common 3D datasets that are purposefully geometrically aligned, real-world imaging rarely shares a common coordinate system and often displays different domains. Moreover, real 3D images can contain diverse topologies where objects can be transformed in different ways. For example, a pair of shoes stored inside a suitcase can be located at any position, occluded or even squeezed by other denser or less dense objects. All of these challenges difficult the translation of real-world imaging modalities. Our method consists of two stages. First, separately, we encode 2D and 3D data points using vector-quantized autoencoders. Each encoding is quantized by mapping to the closest element in a rich information codebook. Then the discrete latents are decoded using a convolutional neural network. Compressing each domain independently eliminates the need for spatially aligned 2D and 3D images. In addition, it allows for both fast and high-resolution image synthesis, where both networks can be trained and verified separately. In the second stage, we perform 2D to 3D translation by modeling the conditional probability distribution in the learned vector-quantized space. For this, we use an unconstrained transformer to parameterize the denoising function. First, the 3D latents are gradually masked out by a Markov chain. The reverse of this diffusion process unmasks the latents using another Markov chain conditional on the 2D latents. We find that our approach enables full coverage attention over the complete information 2D codebooks from a few views, significantly improving the synthesis of new 3D images, where any part of all the 2D inputs can contribute to the voxel predictions. To demonstrate the applicability of our approach, we conducted a set of experiments of two datasets, portraying different topologies and domains, including complex volumetric imagery from publicly available chest CT scans and security baggage screening. We evaluate using density, coverage, and traditional distortion metrics. The model is shown to give a state-of-the-art performance over competing methods, including GAN-based and NeRF-based approaches. Our results show that the identity of each of the bags and suitcases is accurately modeled by our model, specifically latent representation of denser structures as indicated by darker colors, which aligned with real-world scenarios, where denser objects are more likely to be prohibited compared to less dense items such as clothes. In contrast, the other models depict blurring for both dense and soft structures, making it challenging to distinguish them. In the medical domain, our approach achieves a greater degree of precision in modeling and disentangling soft tissue and bone structures. This is evidenced by the distinctive colors employed in the renderings, with a purple tone denoting soft tissue and a beige color representing bone. By contrast, other methods produce blurred images where anatomical structures overlap, and as a result, densities cannot be accurately modeled. Samples from our approach are less noisy, while the other models are only able to reasonably predict some parts of the volume. To summarize, our contributions are a novel and simple translation approach based on conditional diffusion using transformers, generating high-quality 3D samples conditional on two 2D images from a different domain. We showed that diffusion in the information-rich latent code space not only allows for our model to scale easily to high resolution, but also allows for translation of unaligned inputs, as our full coverage attention on latent encodings permits any part of all the 2D inputs to contribute to voxel predictions. The model is shown to give a state-of-the-art density and coverage over competing methods, such as GAN and neural radiance fields, while offering true likelihood estimates.